Welcome to the Royal Astronomical Society on this balmy evening in January. Thank you so much for coming out and
Hi. 1 second. Hello. It sounds like it's gone. Test.
Yep.
No.
Yep.
No, it's still there. There it is. It was hiding from me, and now it's gone. All right. Just get back soon. I know it was there, but I can't find it. No, don't do that. Okay.
We're good.
I think so, but I don't see it sharing, so. Okay, you try that.
Well, that'll teach me to be ironic about the weather. So, but thank you for coming out. We are. I have some house rules. You can see I'm a bit rusty. It's January. I haven't done this for a while, and at lunchtime I did do this. But if the fire alarm goes, we're not expecting a test. So just exit the way you came in, into the courtyard. That's the way out of the building. If you need to use the loos, they are down that way and down the stairs. So my two things. That's number one. Secondly, before I get round to Mike, I would just like to thank Lucinda, who organises the programme of public lectures for the RAS. Pam, who is sitting here and will be taking online questions today. Well, I'm working the mic. And Jessica, who promotes our programs, and some of you may be here as a result of her efforts. So thank you to the RAS team. So, on to Mike, our very distinguished speaker this evening. Now, Mike, as you can see, and again, I forgot that this was standing behind me, and you can all read, I'm sure, is the RAS president and a very distinguished scientist. And as well as being president of the Royal Astronomical Society, he is also a fellow of the Royal Society, which only the most distinguished scientists get to be. So Mike's a professor of space environment physics at the University of Reading. And he has researched how the sun influences near-Earth's space environment and how those interactions have changed over recent centuries. He was previously chairman of the governing council that runs ice-cap radars in northern Scandinavia, which, amongst other applications, can monitor space junk, which the talk is about. In particular, these radars directly observe the large increase in debris generated by a Star Wars missile test on a defunct weather satellite, which Mike is going to talk about later. So, I have practiced my pin to pause for the title. We need to talk about space junk. Thank you. And so Mike is a leading expert in space environment physics. And he's going to tell us all about the growing issue of space junk and its potential impact on the future of space exploration and use. And after the lecture, there will be time for questions. So without further ado, do come along and tell us all about it, Mike. Thank you. Thank you.
Thank you very much, Phil. Okay, so space, the final frontier, right? That's a phrase that's burned into the consciousness of people my age, at least, because of course it was one of the opening line of every Star Trek episode. And Star Trek, we need to remember, was entertainment. It was sometimes very uplifting and the like, but it was fiction. It was entertainment. And what the Star Trek writers very cleverly did with that opening line was invoke something that goes back a long way. It was used by Kennedy when he fired the starting gun that started the space race. And it's actually an idea that goes all the way back to this man, Frederick Jackson Turner, who's an American historian who came to fame because he wrote really no more than an essay, it wasn't even a book, in 1898, about the frontiersman and woman, about frontier mentality, about frontier thinking, and it was incredibly influential. It almost formed an American history. It formed a social glue for America. It was very important. And in the years that have gone by, there have been lots of discussions about it, not all of them positive. Not everybody agrees with what he was saying. But I'm not going to boldly go, there you go, another line from Star Trek, where they went and discussed that. However, there are issues, and in the 100 years since he wrote that mythology, if you like, of frontiersmen, we have been able to study it in a broader context, in other areas and in other contexts. And in particular, I'd recommend this book to you. Carina Keskitalo is a academic in Umeå University in Sweden. It came out last year, it's won prizes, and the publishers are very kindly made it available publicly online. I do recommend it. And she gets it too. Like me, she understands the romance and the admiration for those people that went to the edge of civilization and the border between civilization, the frontier between civilization and the wilderness. But one of the many points she makes is that frontier mentality and frontier thinking can become inappropriate, and it just doesn't apply anymore. And that tends to lead to unsustainable behavior. It tends to lead to rather irresponsible behavior. And she makes those points very well. And for me, space isn't the final frontier. Space is actually a very valuable and fragile resource. It's not a frontier because we're already there. We already use it to an enormous degree. Now, this is a list of applications that I'm not going to go through. I could think of at least doubling it in length. There are two things on this list that have in common. The first is they all improve human life. They all add quality of life. And in some cases, they actually save human lives. Okay, so they're very important things. The other thing that they have in common is that they are all existentially threatened by space junk. And I really mean that they really are threatened by space junk. So for me, it's not a frontier anymore. It was, but it's not a frontier anymore. It's interesting how frontiers don't last that long. The Wild West, probably the most famous frontier, it lasted about 20 years in history, that's all. It's a very short period. It lived much, much longer in the minds of Hollywood film producers than it did in reality. So space, for me, is this valuable and fragile resource and not a frontier. Now, to understand this business and why it's so fragile, I have to talk about hypervelocity. Now, it sounds like I'm going back to Star Trek again, warp factors and all that. I'm not. Hypervelocity is a real concept that we use, and it means anything above about 3 kilometers a second. Okay. And if we compare that to things that we know that are fast, for example, a top whack on a flat out Formula One Grand Prix car is about 1/30th of that threshold. Okay. The fastest fighter jet is about 1/3 of that threshold. And even Mark Cavendish is actually slower than that. Okay, actually by a factor of about 150. My point is this, is that nothing in our experience is anything like hypervelocity. And that's a very good thing that we haven't experienced hypervelocity. I shall explain why in a bit. It's completely odd and alien to us. So now, when I was touring with the family once in France, saw a sign like this, not this one, but beside the road. And it's a road safety warning, if you like. They obviously don't have relativistic cars in France, by the way, because if you were traveling at the speed of light or near it, then this equation wouldn't apply. But for hypervelocity velocities, it still applies. And what they're saying is that your energy, and therefore the energy that would be dissipated in a crash, is in a collision, goes as the square of your speed. It rises not linearly with your speed, but as the square. And in space, in near-Earth orbit, we can quite easily get velocities of 18 or 20 kilometers a second. Okay? And these are hypervelocities. So what does that mean? Well, I'm going to use that equation to look at the energy of a grain of sand. Okay? 10 milligrams grain of sand. And with velocity as it goes up, you get this squared rise in the energy. And when you get up to the sort of velocities that are possible in near-Earth space, then it has more energy than a bullet fired from a high velocity rifle. Okay? And when you look at some things that have been returned from space, these are all solar panels, that look like they've been shot with a high velocity rifle. These look like bullet holes. They're not. They're the holes made by single grains of sand, tiny, tiny micrometeorites. And this one here on the right is actually a panel from the Hubble Space Telescope that was brought back in 1993 as part of the shuttle refurbishment mission of the Hubble Telescope. And you can see it looks like someone's been firing a gun at it. In fact, the other of those panels turned out to have warped so badly that they couldn't fit it back into the shuttle. And so they actually had no option but to do this, and that was literally throw it overboard from the space station. An astronaut, Katie Thornton here, is actually doing just that. She's just throwing the thing into space. It became space junk. Okay? Incidentally, if a grain of sand hitting her would be like a bullet hitting her from a high velocity rifle, a fleck of paint, which is 10 to 100 times more massive, would be like a cannon hitting her, a shell hitting her, okay? And that's why it's a good thing that we don't have any experience of hypervelocity. It's very damaging. Just how damaging? Well, if I go back to this graph and add another one, I've changed the scale, so the bulletin's now barely getting off the horizontal axis. But I've taken a tiny little washer for a bolt, 0.35 of a gram, and you can see it considerably exceeds the energy of a bullet. And if I take a 1 centimeter cube of aluminium, so a sugar cube of aluminium, and take that up to hypervelocities, we exceed the most energetic hand grenades that exist. Okay, so a tiny 1 centimeter cube at these velocities will do more damage than a hand grenade. And that takes some thinking about. And this is why space is so threatened, because there are hypervelocities around. Interestingly, a good definition of hypervelocity would be move fast and break things. And that does actually come from frontier thinking, that expression. It was actually first coined by Mark Zuckerberg, who would see himself as a frontier man on the frontier of cyberspace. And the early Facebook motto was move fast and break things. And it's become a motto that is used as a political strategy now in many areas. Okay, but hypervelocity really does move fast and break things. Okay, let me talk about space a little bit and where we put satellites. And I can deal with these quite quickly. These are the Lagrange points, the Sun-Earth Lagrange points. And let me take L1. L1's simplest to understand. It's where the gravity of the Earth and the Sun balance out. And we can sit in orbit around it. And that's very useful. A satellite there can monitor the Sun. It can look at what the Sun is throwing at us and things like that. L2 actually sits on the other side of the Earth, away from the Sun. And that's really useful for astronomy, because if you look away from both the Sun and the Earth, you've got the noise sources behind you, and you get nice noise-free pictures. And that's why the James Webb telescope is there at L2. Now, these variations in the gravitational field that make these orbits possible are actually very, very shallow. And in fact, we have to spend a bit of energy to keep satellites orbiting around them. We call them halo orbits. And so it only takes a very small amount of propulsion energy, what we call delta V, to send them on a trajectory and get them to crash into the Sun. So we have an easy way of getting rid of things once they're no use. And they're not very cluttered parts of space. There aren't that many astronomical missions. There aren't that many solar observation missions to actually clutter up the space. So this is not a problem. I'm not going to worry about it. Again, it's nothing like the problem that we get when we move closer to Earth. Now, every orbit around the Earth can be described by 6 parameters. Don't worry, I'm not going to go through them. I'm just going to highlight 2 of them. One would be the eccentricity of the orbit. So we can have apogee, the furthest distance from the Earth. That's the spacecraft will be moving very slowly there compared to the average. And then perigee is closest approach to the Earth, and that's where it's moving fastest. Okay, so it can move faster at perigee. The other thing I want to note is the plane of the satellite orbit can be inclined to a reference plane. This is let's say, the equatorial plane of the Earth. And the angle between them is I, the inclination. So if I is 90 degrees, we have a polar orbiting satellite that goes over the pole, one pole and then the other. And if I is 0, we have an equatorial orbiting satellite that goes around. Okay. And those are the only 2 parameters I'm going to look at. And in fact, I'm going to make it simpler than that, because I'm going to think about just a circular orbit, because all the principles are established by circular orbit. So the eccentricity is 1. Now, in this talk, I'm only going to use one equation, I promise. But it's a very simple equation, and it actually gets to the physics of space junk incredibly well. And the equation is that of circular motion. It is that in this context, the gravitational force on the spacecraft caused by the attraction to the Earth supplies the centrifugal acceleration that keeps things moving in a circle. Okay, so it's just Fc equals Fg for a circular orbit. That's actually very useful. We can make it a bit more complicated by actually quantifying those terms. You may remember from school, the centrifugal and centripetal accelerations are mv squared over r. And then we can equate that to Newton's gravity law, which is on the right-hand side there. And then all I have to do is divide by the mass of the satellite over the radial distance r, and do a little bit of rearranging, and I get a nice simple equation for the satellite velocity. And what's interesting about this is that this term here, r, if that decreases, gets smaller, then the velocity gets higher. So satellites close to the Earth move faster than those further away. And then what happens if we slow the satellite down a bit? Now, this will happen naturally, because although they're orbiting in a very good vacuum, there are still particles there. There's still a neutral atmosphere. We call it the thermosphere. And every so often, the particles, the molecules or atoms in the thermosphere will hit the spacecraft, and it's like wind resistance of a car. It slows it down. Or we can slow it down ourselves with a motor that pushes against the motion. I'll come to that in a moment. But if it slows down, then Vs has decreased, and immediately the gravitational force, Fg, is exceeding the centripetal acceleration. And the satellite will fall back towards the Earth. It drops in altitude. Paradoxically, that means it actually starts going faster. So it's kind of perverse. You slow it down and it goes faster. But what it's done is it's turned its gravitational potential energy into kinetic energy. So that's why it's going faster. And when it's down at that lower height, two things happen. Firstly, the atmosphere is a little bit denser because you're closer to Earth. So the frictional drag will be a bit greater. So it will slow it down a bit more. And also it's moving faster. And the frictional drag goes with the velocity squared. And so we're into a vicious circle. This thing is going to keep on dropping. And it follows sort of, I hope, there it goes, a spiral path until it gets to the very bottom of the atmosphere where it probably burns up, but it might come through and actually hit the surface of the Earth. Okay? And that's all come from that very simple equation. Now, we can go a little bit further with that equation for the velocity. If I plug in the numbers for the gravitational constant and the mass of the Earth, altitude of, say, 700 kilometers, I get about 7.5 kilometers per second for the velocity. So if I have a head-on collision of two spacecraft, that's 15 kilometers a second. We're well into the hypervelocity range here. And of course, if it's an elliptical orbit, it could be going a bit faster near a perigee near the Earth. And so 20 is easily possible. And you'll notice I took those graphs up to about 20, about 18, when I did the hypervelocity graph. So we really can get these, we do get these sort of velocities in orbital dynamics. The other thing noticed is the time period. The orbital period of the satellite is the distance, which is the circumference, 2 pi r, divided by the speed. Put in that equation for the speed, and we get this equation for the time period of the satellite. And for a satellite at, say, 800 kilometers, we get about an hour and a half. Okay, so that's low Earth orbit. Things go around every hour and a half. If I go right out to 6.6 Earth radii, radial distance, so a height of 5.6 Earth radii, then I get a period of 24 hours. And that's incredibly useful for an inclination of 0. In other words, a satellite that's going around in the equatorial plane, because it means the satellite stays above exactly the same bit of the Earth, follows it round. And that's incredibly useful for all sorts of applications, like we call it geostationary orbit. We use it for broadcasting and Earth observation, all sorts of things, meteorological satellites. And that popularity of GEO makes it a very, very crowded area. There's an awful lot of hardware sitting in the geostationary ring, both defunct satellites and operational ones. So we have these three areas where we do have to start to worry about space junk. We have low Earth orbits that are nearly circular. We have geostationary orbits in the equatorial plane where things rotate with the Earth. We can have elliptical orbits that go out to high apogee, and we particularly like, in space science, we particularly like elliptical ones that have apogee high over one pole, like this, and we call that a high inclination MEO, mid-Earth orbit, okay, opposed to LEO, which is low Earth orbit, and GEO, which is geostationary orbit. And we can have a medium inclination satellite, and that's actually what we use for GPS and things like that. So positioning and navigation satellites tend to be in those orbits. And we have to think about the space junk for all of those orbits, and it's different. So where does space junk come from? Okay. Well, collisions is an obvious thing. Collisions between spacecraft, they could be operating spacecraft, they could be defunct spacecraft. They could actually be debris from previous collisions colliding with the spacecraft, making more debris. Okay? And there are other things to collide with. There are rocket stages that are just floating around up there, orbiting around, fuel tanks. Pardon me. And actually, you don't even need a collision to actually destroy a spacecraft in space. They explode of their own accord. They can have a little bit of liquid left in a tank, and that vaporizes, the pressure builds up, and the tank explodes. Or a battery can actually cause an explosion. They quite often destroy themselves and break up into bits. So that's another way we get junk. Some satellites vent fluids or gases, they freeze and form ice crystals, and at hypervelocities they can be incredibly damaging. Even space dust particularly causes paint flecks to come off the spacecraft. As I've mentioned, paint flecks are incredibly damaging. Okay. The impacts by micrometeorites are not uncommon, but meteorites are very rare that we actually get hit by a meteorite, but it can happen. Tools dropped by astronauts on spacewalks. It's rare, but it's happened. Okay, I'll come back to that. Deliberate destruction. Okay, so-called Star Wars tests, where you test out whether you can shoot a satellite down. They're very rare, but there are two notorious examples. And publicity stunts. Okay, very, very rare, but completely unnecessary. Why add to the space junk when it's such a problem already? I'm going to show you a movie. These are made by NASA. They're completely realistic. Okay, everything's been done in a realistic and simulated way. The first is an explosion on a defunct craft. The second is a satellite that is damaged and lost because of a small bit of debris, by which I mean probably something about 1 centimeter across. And it's pretty mortally wounded by the damage, but it also tumbles out of control, so you could no longer communicate with it and control it. And then the third is a satellite that's utterly eviscerated by a medium-sized bit of debris, 10 centimeters long. Okay, so let's have a look at those. Don't blink, it happens very, very quickly. So here's a defunct satellite. It's already falling apart, bits are falling off it, but then a tank explodes, and okay, we've got lots of debris. We've got something that can go on and generate more debris by hitting something else. It's completely uncontrollable. We can't communicate it with it anymore. Here's the small bit of space junk. You might have seen it come in. Okay, again, completely uncontrollable spacecraft. Here's the medium-sized bit of junk. And okay, now you understand why I say it's a good job that we've never had experience of hypervelocity. Okay, there were relatively small things that did all that damage. So we divide space junk up into small, less than 1 centimeter. Can be flecks of paint. We estimate there are about 130 million such pieces in low Earth orbit alone. It can be dust from rocket boosters, even that is damaging, ice, all sorts of things. Okay, small. Medium we take to be 1 and 10. These are normally small products of collisions. Okay, and we think there's about 1 million of them in low Earth orbit. And large, which are bigger than 10 centimeters. Okay, and we know how many there are. We track them using radars, and we last count, which was a few months ago, is 37,000 of them. Okay, just in low Earth orbit. That, unfortunately, is not the end of the story, because there are also ginormous, huge bits of space junk up there. This is a satellite called ENVISAT. It was launched by ESA. It was an environmental Earth observation satellite. On the surface of Earth, it weighed 8 tons. It's bigger than a coach. And so these guys working underneath it are braver than I am. It was launched in 2002 to an altitude of 800 kilometers. It did some great science for a decade. and then it died, almost certainly because it was hit by a bit of space junk in a rather crucial area. And it's still up there, going round and round, okay, completely useless, but very large and very heavy. And if we just leave it alone to re-enter, it will take 150 years before it comes down to the surface of the Earth or the lower atmosphere. 150 years. And you think, okay, well, it's longer than my lifetime, let's not worry about it for now. Unfortunately, we do have to worry about it because twice every year, a sizable object, a satellite or a sizable bit of satellite debris, 2 of them pass within 200 meters of it every year. We are going to get a collision sooner or later. That's going to be a shower of debris and things. So let's look at the rise of space debris since Sputnik, the first satellite. So in black, you have the total number of things that we know about in orbit. So this is large debris and an actual working spacecraft. The actual operating spacecraft, sorry, people online won't be able to see that, is this blue line. So these are actually active satellites, okay? So most of the stuff out there is not active satellites. And you'll notice the big turn up at the end. This is the commercialization of space. This is Starlink and things like that. And that's reflected in the total number, although the debris has risen a bit too in recent years. So now I want to take a look at these sudden steps in the total number, which is actually a step in debris. We can see that. And there were 2 of them. And the first one you heard a little bit about from Phil, and that I had helped and manage the design and building of this radar on Svalbard, Spitsbergen. It's an island halfway between the North Pole and the North Cape of North Norway. And it's really a radar for studying the upper atmosphere, the thermosphere, the ionosphere, and aurora, okay? But it can also detect space junk. And to start with, while we were still getting it up to stream, we were looking at the space junk by pointing the thing north, and we would see this sort of, oops, I've gone the wrong way. We would see this sort of thing. So each one of these red dots is a bit of space debris going by. We could measure how far it was from the time the pulse reflected took to go to and come back to us. And red is red shifted, it's Doppler shifted, so it's moving away from us, and blue is blue shifted, it was moving towards us. So we've got a mixture of all of them. We've got some moving at 90 degrees to the radar beam that show up as grey or green. And that was, we've got several days of data here, and that went on kind of every day. And then it changed, and it changed to this. And we started to see a band of stuff coming towards us, and then a band going away every day, repeating. Okay? And we worked out that it must be something like this, that we had a band of new junk going around. And what was happening, we were looking north, and when we in position A, we would see it coming towards us, but a few hours later, we've rotated round, but the band hasn't, and we're seeing it go away. And from the height and the orientation of that orbit, we worked out what it was that had produced all this. And we came to the conclusion that it must be this Pengyung IC, a defunct Chinese meteorological satellite. Now, we're pretty pleased with ourselves, but it turned out we weren't the first people to work this out. The people that tracked space junk got there before us. They knew what it was, and they knew what had happened. And what had happened was that on January the 11th, 2007, the Chinese conducted a Star Wars test with what's called a kinetic kill missile, just a lump of metal crushed head on into it to hypervelocity speeds. And it destroyed it. Okay? Incredibly irresponsible thing to do. I'll show you just how irresponsible in a bit. But it wasn't even necessary. They didn't need to test the technology. They knew they could do it. What it really was just saying, we can do this, you know. Okay? It was announcing to the world that they had a Star Wars kill capability. Okay, again, totally unnecessary and very damaging. Within a couple of months, the people that tracked the debris had catalogued 2,000 extra bits of debris, and that grew and grew. Okay, and it had consequences because in 2013, one of those bits of debris, we were up to 30,000 bits here, it's given a name, Pengyung IC debris, and then a number. and it hit a Russian spacecraft, and that became space junk. Okay, so it does have consequence. The really, sorry, I'm just going to add this just because I'm very critical of the Chinese for doing this. They were only doing what the Americans had already done before. They destroyed a satellite slightly lower altitude, so it won't. The junk doesn't take long to go away, and they used a missile launch from an F-15 fighter jet. But so, you know, the Chinese could say, hey, well, they did it. And it just stresses how responsible behavior is really important. If you want others to behave responsibly, you have to behave responsibly. Why it's so irresponsible is shown by this graph. Okay, this is the decay of that debris, okay, in percentage over the next century. And in 100 years' time, 80% of it will still be there. Okay, it's really hard to get rid of these tiny fragments. Okay, they're lethal for other spacecraft, but are just going to orbit there, and it's going to take hundreds of years to get it out of the atmosphere if we just leave it. But we have no other way of. It's all small bits. It's not easy to deorbit those bits. We have no way of doing it. Okay, so that was the first step. What about the second one? Well, that turned out to be an accident, just an unavoidable accident. What happened was a chance collision of two spacecraft. One of the Iridium craft, number 33, crashed into a Russian craft. Okay. And Iridium is a constellation of polar orbiting satellites in different orbits. It's almost amazing they don't collide with each other. And here's 33, minding its own business, and here comes Cosmos. And this is a simulation based on orbital dynamics and radar observations of the craft before and after the collision. It's going to show it in gory detail a few times. The size of those debris is greatly exaggerated so you can see them. So you can see actually how the debris cloud spreads out. Some bits are smaller, the drag from the thermosphere slows them down quicker. They fall behind and they drop down towards Earth quicker than the larger pieces. Okay. And they'll follow the original orbit of the spacecraft that produced them and just join the mass of other things in orbit. So these are active spacecraft, defunct spacecraft, and space junk in green, and it just fits into the mass. So if space is like that, isn't this dangerous for things like the space shuttle? And the answer is yes, it is. The space shuttle has what we call a Whipple shield. It's a series of baffles that slow an object down. So by the time it reaches the shell of the shuttle itself, it's just splattered out onto the surface and doesn't penetrate it. It's great, but it only works for objects up to about 1 centimeter in size. Okay? It's pretty impressive that it does. But that's it. And every impact causes the shield to deteriorate in terms of what it can stop. Obviously, if something arrives at the same hole that something's already made, it's going to come straight through onto the shell of the craft. So how do we deal with larger bits of junk that the Whipple shield wouldn't stop? We've got no option but to dodge them. Okay, so how do you dodge them? You have people on the ground running radars, monitoring where the junk is all the time, working out when you're on a collision course with one, and manoeuvring the ISS out the way. And the number of such manoeuvres that they've had to do has gone up over time because of the amount of space junk done over time. And this is they. You'll notice it goes up and down with the solar cycle as well, and I'll explain that in a bit. Now, what we fear about all this is something that was proposed in what year? 1978 by Donald Kessler, and that's the scientist. And he proposed that what could happen if the junk gets great enough that the junk from one collision goes on to cause another, which goes on to cause another, goes another. You have a catastrophe where everything is reduced to smaller fragments in space, renders space completely unusable. It's called the Kessler syndrome. Now, yes, it's a theoretical prediction rather than we've never seen it, thank God. But we can kind of model it. It gets complicated. This is actually a relatively simple model where you look at the interactions of all the different sizes of debris. And essentially you have some cycles in here that are balanced, okay, that have no net effect. But you have some that are marked with an R that actually are feedback cycles. They're positive feedback cycles. And so if you get a bit of a perturbation, it makes things worse, right? And that's all driven by this down here, the number of launches of satellites, okay, that you're putting up in the first place. Okay, so that's the driving thing. And all you have to counteract the growth that will cause in debris is orbital decay. And you've already seen how slow that is, particularly for high altitude jump. Okay, so that's the only negative feedbacks that we have come from the orbital decay phenomenon. So it's very hard to get things out of space. And the predictions is that the threat is, it's there, it's going to happen, it's inevitable. If we keep on the way we are, we have to do something to stop the junk growing faster than we can get it out of space. Otherwise, sooner or later, it will happen. And this is actually, would render space unusable. If you put a spacecraft up, it would be destroyed in a hypervelocity collision incredibly quickly. And also, for those that still like the frontier idea of space, if there is a frontier, it's Mars. It's not near Earth space. And so this junk would be like a cage, because you would be able to see Mars, you would be able to see your frontier, your wilderness on Mars, but you wouldn't be able to get there, because if you tried, you would be destroyed by space junk on the way. Okay, so we would be held captive by our own junk, basically. And that's a thought that people that like the frontier idea need to think about. So what can we do to try and avoid this? Well, we have some strategies, not many. I'm not going to worry about deep space for the reasons I've already explained, but let's look at GEO. We do have a strategy there. What we do is we try to keep old satellites with a little bit of propulsion, jet fuel or whatever left, delta V we call it, so we can move the spacecraft out of geostationary orbit to a little bit and park it a little bit further out in what we call a graveyard orbit, okay? And we just hope that the explosions and the collisions there don't send debris back towards geostationary. It hasn't happened yet. So it's a strategy that's working for the time being, but it's probably not sustainable in the long run. For mid-Earth orbit, we have no clear solution as yet, okay? But it's not such a crowded area, although it's getting more crowded because of GPS and other navigation systems. And for LEO, all we have is deorbiting, okay? Now, we can leave that to natural deorbiting because of the frictional drag of the atmosphere. I'll tell you the problem with that in a bit. Or we can actually do something about it, okay? We can actually try and slow the spacecraft down, not with frictional drag, but capturing it and actually slowing it down, and that will cause it to drop. And if we do that in a controlled way, we can make the thing finally re-enter it in a place where it won't do any damage. And actually, the UK has tested a mission called Remove Debris, and it's this one here. It used a net to capture something and then slowed it down, dropped it. It came back up, and what it captured was deorbited. There are other possibilities using magnets to try and hoover up all the small fragments of at least magnetic metals. ESA is working on this rather sinister looking thing that has tentacles to grab hold of something. Again, slow it down so it drops, but then has enough fuel to save itself. And for other materials, people are looking at harpoons to try and capture things and do the same. I should say there is a snag to all of this. Okay, you know, you're getting rid of the debris. We have now detected that the amount of metals going up in our stratosphere is going up quite rapidly. And we have no idea what metal pollution will do to the stratosphere, what it will do to the ozone layer, for example, what it will do to climate, because you can get stratosphere-troposphere interactions that affect climate. So again, we're running an experiment we just don't understand by putting metals into the stratosphere in these quantities. So it's relatively recently we found out just how much it was going up. And there is a risk beyond space of all this, and that is things can fall through right to the surface of the Earth. Just December 30th this year, this ring dropped nearly onto a village in Kenya, just outside the village it fell. Now, it's been questioned if it's actually space junk, because it's not very charred. On the other hand, it was red hot when it was first found, which implies it's been through the atmosphere and all of the atmosphere. And secondly, around the village, all around the village was found bits that were definitely space junk. So it almost certainly is space junk. And everybody's denying ever having seen it before. All the space agencies says, oh, no, we've never launched anything that looks remotely like that. So there's everybody's claiming never to have seen this before. Somebody has, but everybody's claiming not to have. And all the space agents are saying, oh, it's not us, not us. One of the favored theories is that it might be a ring that separated two geostationary satellites during launch, but then went on to geostationary. And that would have been a launch of an Ariane 5 18 years ago. So this thing has been lurking up there. If that's right, Ariane deny it, but if it has, it's been lurking up there for 18 years before it fell out the sky on Kenya. And there have been other examples. There's a family now living in Florida who is suing NASA after their house was destroyed in California. And it turned out to be a battery that came from the space station. Whether it was dropped or thrown or fell or whatever, we don't know. But it went through the roof of their house, it went through the first floor of their house, it went through the basement of their house, and it made a 2-meter hole in the ground underneath the house. It missed the young boy who was playing by a couple of meters, and the father was in the house at the same time too. And this is a really interesting case because the whole business of who's responsible for this, it used to be nation states, but now with commercialization, who's responsible when space junk comes to Earth? SpaceX rocket parts have been found across Canada and North Carolina. And actually, Qantas have actually cancelled quite a few flights because they say too much space debris is falling towards Earth in the southern hemisphere, and they blame SpaceX for that, reported by Euronews. And the recent incident of a SpaceX rocket blowing up caused all flights to the Caribbean to be diverted. Okay, so there is this risk lower down as well as to space. Now, I need to explain something about space weather, because space weather produces these wonderful auroral events like we've had recently. We get aurora over well-known locations in the UK, like Stonehenge and the Angel of the North. And they're very beautiful, but they also heat up the thermosphere. And this is a simulation of the ionosphere-thermosphere system during one of these large geomagnetic storms. You see the auroral regions near the pole getting heated, but it spreads around the globe, okay? These darker areas are heated areas of the atmosphere. And that causes the atmosphere to well upwards, because it's hotter. That increases the density that every satellite is having to go to. That increases the drag, and it speeds up re-entry, okay? And if you're a small bit, it probably causes you to actually go into the final re-entry. So, the thermosphere, this sort of heating happens on all sorts of time scales. And it's a worry. For example, at ISS, you're trying to dodge bits of spacecraft, or bits of junk rather, and then their orbit is all changed. Okay, we've got to find out what this changed to quite quickly so that we don't allow a collision to happen. And there's a famous example of what thermospheric heating did to Skylab, because Skylab was designed to fall down in altitude, but then be pushed back up by the space shuttle. But the space shuttle wasn't ready, and the solar cycle was more active than predicted, which meant there were more of these geomagnetic storms that heated the thermosphere, and Skylab fell faster than expected, and there was nothing to put it back up. And so this was it had no fuel to help itself back up. And this was a completely uncontrolled re-entry. Okay, we were relatively lucky. We were actually living in New Zealand at the time, and the news items were, "Oh, it's passed over New Zealand today, thank God." And it came down in the end in the Nullarbor Desert in Australia. But it was uncontrolled. We had no control over it at all. Okay. Now, 3% of Earth's surface is actually populated, so the chances are it was going to fall safely. Okay, but if this keeps happening, sooner or later, something's going to fall where we don't want it to. So when we deorbit, we've got to be careful. And what happens when you deorbit is things like solar panels get blown off quite quickly, and they re-enter quite quickly. And then the main module will rupture, and you'll get the debris from that. And then the core will carry on, and that's the last thing to come down. Okay, so you get this trail of debris along the orbit path. Okay, and when we re-enter something, we want to try and make that as short as possible, and we want to make it over an unpopulated region like the Southern Oceans or something like that. But to do that is actually quite difficult because of this thermospheric effect. So this shows you the density profile of the thermosphere with altitude for a hot thermosphere. I'm sorry, the writing's got covered up here, and a cold thermosphere. Okay, and it's much, much denser at higher altitudes when the thermosphere is heated up. So what does this mean? Well, we can do simulations of orbital decay. So if I just take the top panel, the altitude, for the hot satellite starting from the same altitude, it enters, re-enters. And once it's fallen to about 190 kilometers, it's coming down quickly. So we call that the re-entry altitude. For the cold thermosphere, it takes a lot longer before the same thing happens. Now, this difference is about 5 orbits. So it could have happened anywhere along that. If we didn't have the thermospheric predictions to tell us where we want it to drop, then we wouldn't know how to deorbit to make it drop in a safe place. So we have to also understand the state of the thermosphere and how hot it is, and how long it will be before a deorbit maneuver actually causes re-entry. And so it re-enters in the right place. Okay, so it gets more and more difficult. We've known this science for a long time. We knew it with the first artificial satellite, Sputnik. Sputnik did nothing but beep. It just sent a message to America. It just said, we can do this, beep, beep. That's what the message was. That was the only point of it. Didn't have any instruments on it or anything. Didn't even have any telemetry. And what we could do is we could watch its orbit period. And what we found was from the orbit period, we could measure the atmospheric density, and we found that it rose significantly during, this is a geomagnetic index, AP, that tells you the state of the space weather. And we found these space weather events was causing the upper atmosphere to heat up just by using the orbital decay of Sputnik. Right, lastly, I just want to say something about Starlink, because Starlink is a commercial internet provider that's aiming to provide global internet service. At the moment, there are 7,000 Starlink satellites in orbit already. There are immediate plans to raise that by another 5,000, and they're talking about finally a network of 34,000. Now, bear in mind that Kessler syndrome diagram, it all starts with the number of launches you're doing. So this is a worry, okay? It's a huge worry. At the moment, there are 4 million subscribers, so it's now in profit. SpaceX are very coy about who uses it, but we estimate that about 25% of it is military. There are rivals planned, but not on the same scale. But there are responsible aspects to Starlink. All craft have autonomous propulsion that's used to lift them into orbit, and that's significant. I'll talk about why in a moment. That's at about 500 kilometers altitude. It can be used to deorbit them, and it's also used to maneuver it to avoid collisions, which sounds great. And at the moment, they're using maps of the data of the debris they need to avoid that are provided by the US military from ground-based radars. But in the end, they want to make it autonomous, so it senses the junk itself and gets itself out the way. Sounds a great idea, but it's terrible for everybody else because you might get spacecraft. At least junk stays on an orbit, apart from the odd thermospheric heating event. Whereas if these things start jumping around in front of you, we may get more collisions. And thus far, Starlink satellites have had to make at least 7,000 evasion manoeuvres. But there is a deorbiting strategy with them. I have to add, because we're here at the RAS, but it's an absolute pain in the neck for astronomy, it's causing major problems with light reflected off the underside of the spacecraft. Sometimes ground-based astronomical images are just unusable. And it's an even bigger problem for radio telescopes because of the radio noise they emit. And there are serious worries about the degradation of satellite, of radar, radio telescopes like LOFAR or square kilometer array. Okay. The way Starlink satellites launched is really interesting. This is actually a picture of a stack of 30 of them. They're stacked like chairs in your village hall, okay, your local hall, church hall. And they're released one by one. And that's done it was done at an altitude of 210 kilometers. Now that's very low. Remember, 190 and you're doomed, you're going to re-enter. That's the re-entry altitude. And why that was a responsible procedure was that you could test them. And if they failed the test, you just leave them there. And very quickly, probably in a month or so, they'll get burnt up. Okay. If they pass all the tests, you use the onboard autonomous propulsion to push them up to their final orbit. Okay, and you hold some of that propulsion back to allow them to deorbit. The problem is it's a slightly risky procedure because if you get one of those thermospheric heating events, satellites at 210 are incredibly vulnerable. And that's what happened on February 7th of 2022. When 46 of these satellites, they'd only processed a small number, and 38 of them were lost and re-entered because there was a thermospheric storm. And that's the point, things keep changing. So you've got to monitor the thermosphere very carefully to understand the drag that it causes if we're going to get things. It did provide a glory moment for the Costa Rican Astronomical Society, because they actually captured the satellites falling to Earth from the ground. We get this more close-up view. Okay, so those are Starlink satellites burning up in the atmosphere and adding to the space junk. So my conclusions: space is an incredibly valuable resource. Okay, we use it massively now for all sorts of applications. But it's very fragile and it will not survive irresponsible exploitation. Our future in space is seriously threatened unless we actually pay heed to that. And that is why we need to talk about space junk. Okay, with that, Arthur. Thank you.
Testing. So it's nearly 7 o'clock, Professor Lockwood. You did a really great job, but we have a few moments for some questions. So any questions? Please make sure you people so much. Thank you.
Yeah,
Finally, like unstable conditional climate. So maybe from the difference. It's something. Area. So maybe this some tables. Down to. So maybe like visual moon or something. Form.
but if you're talking about taking something that far away, the problem is the amount of fuel that you need to do that.
Well, you can use it like kind of shovel then or something.
Yeah.
Like a float. Or maybe even just get like something.
If you're drawing a parallel to things like rings around icy giants, then the problem there is they're going the other way. They are large bits that have been pulled apart and they're disintegrating. So I'm not sure they're going to offer a solution, but we wouldn't be able to get away out of far from Earth anyway.
It's something like visual moon out of this job. But the giant travel is more difficult. Travels, dangerous, like, more organized. Like a peaceful island next to so it's like.
But how do you get it there? If we're going to launch it from the ground, it would take thousands of rockets to put it up, and each one of those rockets would put space junk in there. So, yeah. When we spend things into deep space, like missions to planets, then we do tend to crash the spacecraft into the planet, which means that we make a little bit of space junk there. Sorry.
Very quickly, looking at our spotters.
Sorry, I did do the talk earlier in 45, didn't I? I'm obviously tired. I've slowed down.
If there's so much in our orbit now, how are we going to stop this? How do we stop this? This incentive to breathe in how we go, when we get trapped here.
That's the worry. Yes, that is the worry, that we won't be able to use space and we won't be able to pass through low Earth orbit because it's too full of junk. We are taking it seriously, and I'm very proud that the UK is actually probably the first nation to do a capture mission, deorbit something. So that's worked, but it's one bit. And how do we cope with all these little bits? And that's where the magnets come in, but not all that junk is magnetized, so we can't use magnets for all of it. So.
Space junk, that we have falls or failures, and we think we'll be able to do this in the future. I guess it's technology.
Yep. But what we have to do is get the deorbiting rate back down below the rate at which it's going up. And we're miles from doing that at the moment. So while the rates at which we're putting junk up there, and that includes collisions and unintentional junk production, while that exceeds the rate at which it's being taken out of the orbit, we're heading towards Kessler. I have no idea how long it's going to take, but we're heading that way.
So it does. Powerless. Suddenly. With effective long-term observation.
The observations. And again, to be fair to Starlink, they have tried. They painted the underside of the spacecraft black. It didn't particularly make much difference. They fitted a sun shield to try and stop it. Again, it didn't really work. They have tried. It's slightly ironic because the owner of SpaceX has made all the right noises about educating people and having a trained workforce and things. He gets that, and that's great. I agree with him completely. And astronomy ground-based astronomy is such a great way of getting people into science. It's a way of infusing young people to do science. And yet his commercial arm is busy making that impossible. So needs to think about that.
Any other questions?
Especially at home. In terms of regulations, are government bodies actually apply regulation to membership?
Well, there's a sort of rough understanding that a nation is responsible for the government, for the companies, but who owns companies now? The nation idea is not working. It doesn't fit anymore. And you're absolutely right. The international law on space and responsible use of space is suddenly blown into pieces by the commercialization. And actually, this is why people are looking at that court case in Florida so closely, because the outcome of that, and because they're blaming NASA. Okay, now it's not even, the space station is not just NASA. It's joint with the Russian Space Agency as well. But we have no idea how that bit of junk ended up coming through that house. But if NASA do successfully sue NASA, that will set a precedent that anybody who contributed to that problem is actually liable. So that would be a start, but we have a long way to go. And that's just in the American courts, how that translates to international action. It's a minefield of an area. Yeah, I'm not an expert in it, but I know it needs revamping and it needs urgent attention, basically.
Thank you. Back to the how is with space sort of thing on the observation. Is there any or maybe just always the most do or is there any way to get along to
I can't answer that. I mean, at the moment, there are 7,000 up there, and they want to end up at 34,500. So it's going to be very hard to see how we can do any ground-based astronomy under those conditions. At the moment, it's a major nuisance. There are ways around it. Instead of just integrating over time, you can slice it up a bit like your mobile phone does, take a lot of pictures and then integrate them. And if a bit of noise, if a Starlink satellite goes through, you throw that frame away. So there are things that we can maybe do, but it's making it difficult. But if there's always Starlink satellites there, then that doesn't work. So, yeah. I'm afraid I'm not great on solutions. I'm one of those people who can tell you all the problems, but I don't have the solutions.
Okay. Is there any sort of vaporizing these small pieces where something will be?
Yeah, no, lasers have been talked about. Yeah, they have. Oh, sorry, the question was, can we vaporize material using, say, laser beams? And that has been investigated, yes. I think the problem is you need a rather large and powerful space-based laser, which is, going to cause a lot of junk, put it up there. So, yes, that is one of the problems. A lot of the solutions produce as much junk as they remove.
One question. If we encouraging deorbiting stuff, if that's what we want to happen, also saying that metal pollution, strategy, then is that very urgent and is there any way that if the deal is shove the satellite to the start? Funding into research.
Yeah, no, that would be great. But again, we need the international law to enforce that. And you know, it needs to be international because the companies doing it are now international. So it's hard to deal with. On the metals in the stratosphere, I should stress that is a really recent result. That's only been known a couple of months now. And somebody I know, John Plain from Leeds, was one of the people. It was a NOAA spacecraft, a satellite aircraft, the high altitude aircraft that detected, that flew up into the stratosphere. And we'd never seen metals, and they're definitely the sort of metals that are used in spacecraft technology. So we know where it's coming from. It's just another thing to think about. In terms of deorbiting, though, getting things from low Earth orbit, there's no way we can supply them with enough delta V, enough fuel propulsion to kick them out. So our only hope is to drag them down and let them burn up in the atmosphere. So, but you're right, it's not great. It's not a planet, it's not an ideal solution, but yeah, if we want to keep exploiting space, we have to find a solution.
It falls to me to draw this evening to a close. I'm sure you've all found Mike's talk incredibly thought-provoking and informative, and we should thank him for taking the time to talk to you this evening. Thank you, Mike. And maybe Mike will hang around for a very few minutes for questions, but we've worked him very hard as president today, and he really has earned his dinner, so don't keep him too long. Thank you. Thanks, Mike.
Yeah, so my pleasure. It is good. There are layers of functions. Slightly worried. As I say, I'm not. Are you? I'm a bit of both. We do need to get rid of this frontier. That was really we're not going to that was really a dig at the PayPal idea because